1 nanosecond of clock error moves your dot 30 centimeters off. That's because radio waves travel about 30 centimeters in a nanosecond. So how does a phone pin itself to a few meters using clocks floating in space? Here's the thing almost nobody realizes. GPS never measures where you are. It measures how long a signal took to get to you. Distance equals speed times time, and these signals move at the speed of light, about 300,000 kilometers per second, roughly 30 centimeters every nanosecond. So a tiny timing slip becomes a real location error. The whole system lives or dies on nanosecond timing. Start with the machines doing the broadcasting. Right now, somewhere between 24 and 31 GPS satellites are circling Earth. They sit in medium orbit, about 20,200 kilometers up, far higher than the space station but nowhere near the moon. Think of them as a fixed scaffolding wrapped around the planet. They're arranged so that from almost anywhere on the ground, several are overhead at once. Each one is doing something almost boringly simple. It shouts. Continuously, every satellite broadcasts a signal that says two things. Exactly where I am in space, and exactly what time it is right now as I send this. That's it. Position and time over and over at the speed of light. Now here's the part that surprises people. Your phone never talks back. It has no transmitter aimed at orbit, no handshake, no request. It just listens. The satellites don't know you exist. They don't know how many phones are down here, and they don't care. This is why GPS works for millions of devices at once with zero strain. A radio station doesn't slow down because more people tune in. Your phone is a passive receiver, quietly catching signals that were already being broadcast to everyone. But if your phone only listens and the signal just says where and when, how does that turn into a location on a map? For that, we have to do a little geometry. That covers the what. Now the how. Your phone catches a signal and reads the timestamp inside it. This left the satellite at such and such moment. It checks its own clock for when it arrived. Subtract and you get the travel time. Multiply travel time by the speed of light and you get one number, how far away that satellite is. Say it's 21,000 kilometers. What does that one distance tell you? Not much on its own. It means you're somewhere on the surface of a giant invisible sphere. 21,000 kilometers in radius centered on that satellite. You could be anywhere on that shell. So the phone listens to a second satellite and gets a second distance. A second sphere. Two spheres don't touch at a point. They overlap in a ring, a circle where both are true at once. Better, but still a whole circle of possible spots. At a third satellite, a third sphere. Now 3 spheres intersect, and 3 spheres meet at just 2 points. One of those points is out in space or deep underground, so it's easy to throw away. What's left is you. This is the core trick, and engineers call it trilateration. Finding a point by measuring your distance from 3 known locations. 3 satellites, 3 distances, 1 spot on Earth. But there's a crack in this story. All of it depends on measuring travel time down to the nanosecond. And that raises an uncomfortable question about clocks. Here's where the engineering gets serious. Remember the number from the very start. 1 nanosecond of timing error equals 30 centimeters of position error. So if the satellite's clock is off by even a few billionths of a second, your location smears out by meters. That means the time stamped inside every signal has to be almost perfect. A normal clock, the kind ticking in your microwave or your wristwatch, drifts far too much. Over a single day, it can wander by whole seconds. At 30 centimeters per nanosecond, that's a catastrophe. So every GPS satellite carries something extraordinary, an atomic clock. 2 kinds fly up there, one built around rubidium atoms and one around cesium atoms. Here's what makes them special. An ordinary clock counts the swing of a spring or the buzz of a quartz crystal, and those can speed up or slow down with temperature and age. An atomic clock counts something that never changes, the natural rhythm of an atom, which vibrates at a fixed, unchanging frequency built into physics itself. Cesium atoms flip back and forth billions of times a second, always at exactly the same rate. Count those flips and you have a clock stable to about a nanosecond, thousands of times steadier than any quartz chip could ever be. That's why the satellites carry them and your phone does not. But hold on. If the satellite has a flawless atomic clock and your phone only has a cheap one, doesn't that broken clock in your pocket ruin the whole measurement? You spotted the flaw, and it's a real one. Your phone's clock is cheap quartz, worth a few cents, and it is nowhere near nanosecond accurate. It doesn't truly know the exact instant a signal arrived. And if the arrival time is fuzzy, every distance you calculate is fuzzy too. So how does a phone with a bad clock still land you within a few meters? The fix is beautiful and it's pure algebra. Think about what you're actually trying to find. There are 3 unknowns in your position. How far east, how far north, and how high up you are. Call them X, Y, and Z. 3 unknowns normally need 3 equations, which is why 3 satellites felt like enough. But your phone's clock error is a 4th unknown. One mystery offset that's throwing off every measurement by the same amount. 4 unknowns need 4 equations. So the phone simply listens to a fourth satellite. Now it has 4 distance measurements, 4 equations, and it solves all 4 unknowns at once. Your position and the exact size of its own clock error together in a single calculation. The phone essentially discovers how wrong its clock is by finding the one clock correction that makes all 4 satellite distances agree. This is why your phone needs at least 4 satellites in view for a genuine fix, not 3. And it's why more is better. Catch 6, 8, 10 satellites, and the extra equations let it average out mistakes and tighten the answer. But even 4 perfect atomic clocks and flawless algebra can't give you centimeters. Something up there is still bending the numbers. Now the strangest layer of all. Those atomic clocks are perfect, and yet they run at the wrong speed on purpose. Blame Einstein. 2 effects fight over each satellite's clock. First, the satellite is racing through orbit at thousands of kilometers per hour, and fast motion makes a clock tick slower. That's special relativity, and it slows the satellite's clock by about 7 microseconds a day. Second, the satellite sits way up high where Earth's gravity is weaker, and weaker gravity makes a clock tick faster. That's general relativity, and it speeds the clock up by about 45 microseconds a day. Add them together and the high-altitude speed-up wins. The net result? Every satellite clock gains roughly 38 microseconds each, and every day compared to clocks on the ground. That sounds tiny. It is not. Remember 30 centimeters per nanosecond. A microsecond is 1,000 nanoseconds. Left uncorrected, 38 microseconds of daily drift would throw your position off by about 10 kilometers per day. GPS would be useless by lunchtime. So engineers build the correction in before launch, deliberately setting the clocks to tick at a rate that looks wrong on the ground but comes out perfect in orbit. And even with all that, the real world adds noise. Signals slow down passing through the upper atmosphere. They bounce off buildings and arrive late, an echo pretending to be the original. That's why your everyday fix lands around a few meters, not centimeters. The physics is exact, the sky and the city are messy. Now watch the whole machine run in one breath. 20-some satellites, each with an atomic clock stable to a nanosecond, each shouting its position and the exact time. Clocks deliberately tuned to counter Einstein's 38 microseconds a day. Your phone, silent, catches 4 of those signals. It reads the timestamps, checks its own arrival times, and turns 4 travel times into 4 distances. Then it solves 4 equations at once, pulling out your position and its own clock error in a single stroke of algebra. 4 spheres in space collapse onto 1 point on Earth. And this is exactly why the number from the opening rules everything. Break time equals 0, 6 is /1 nanosecond equals 30 centimeters. That single fact is why the satellites carry atomic clocks instead of quartz, why relativity has to be corrected, why the whole architecture obsesses over billionths of a second. The entire system is engineered around it. So the blue dot on your screen isn't really a place the phone looked up on a map. It's the answer to 4 equations, timed against atomic clocks orbiting 20,200 kilometers over your head. You are being located by the speed of light and the honesty of an atom. So here's the one thing to carry away. GPS is not a map in the sky. It's a timing system. Everything it does is really about measuring nanoseconds and turning them into distance. Next time your dot drifts in a parking garage, you'll know exactly why. No clear sky, no clean timing. That's the timing trick behind your blue dot. But GPS alone is slow and useless indoors. So how does your phone blend it with Wi-Fi cell towers and the motion sensors inside it to lock on in seconds, even underground? That's the next one.